Hello, my name is Nicholas Adduci, and this is my honors capstone presentation for Youngstown State University, spring semester 2021. My honors capstone is entitled An Investigation into Visual and Geometric Representations of Prime Numbers. And we begin our investigation with the natural numbers. Now suppose we want to look for patterns within the natural numbers dealing with the primes. How can we reconceptualize the natural numbers in such a way as to elucidate these patterns, that they may be displayed visually, that we could actually begin to see the prime numbers at work within the natural numbers? Now we understand that the primes are the fundamental structural unit of the naturals. So if we begin to think about the natural numbers geometrically, perhaps we can illuminate some structural qualities that relate to the primes. And so we develop a new geometric basis for the natural numbers. So consider each natural number as a rectangle, with a factor pair of positive integers corresponding to the sides of the rectangle. Take the number 12, for example. Could be represented by a 3 by 4 rectangle, a 2 by 6 rectangle, or a 12 by 1 rectangle. So it becomes immediately obvious that prime numbers could only be represented by a rectangle of p width and 1 height for prime p. Positive numbers then could have multiple rectangles to represent them. But now if we want this to be our new geometric basis for the natural numbers, we've got to be consistent in choosing a unique rectangle for each number. So how do we go about this? Well, we could take the rectangle of least perimeter. Every number is going to have one rectangle which had the least perimeter. So for each composite number, you choose this rectangle. Take the number 12, for example, in the illustration provided. We have a 3 by 4 rectangle, and we have a 2 by 6 rectangle, both of which correspond to the number 12, but the 3 by 4 rectangle has the least perimeter. So we choose that for the new geometric basis that we're developing. Also note that the rectangle of least perimeter corresponds to the rectangle of so-called least distance between the lower left corner and the upper right corner from the point O to A in the illustration. So just note that for our visual representation, we suppose that each of these rectangles of least distance were placed on a grid so that their lower left corner were common to them. Now for each natural number n, we plot the point xy, where x and y correspond to the length of the sides of the rectangle of least distance, where x is the larger of the two sides without loss of generality. Now what would our result look like? Well, we obtain what's called the LD grid, LD standing for least distance, and we have a specialized function that we've defined in order to formalize our study of this visual representation called the LD function, the least distance function, which is given by LD of n equals the minimum of the set a plus b minus 2 such that ab equals n, where a and b are positive integers. So you take any number on this grid and it's been plotted according to its least distance. It's only been plotted once because each number corresponds to a unique rectangle of so-called least distance. Okay, so take the number 8, for example. The least distance of 8 is obtained from this grid by counting the number of blocks away from the origin. So we go 1, 2, 3, 4. So the LD of 8 is 4. Keep in mind that the LD function is not as much concerned with the actual distance from point A to point B as, say, the Pythagorean theorem would be, but is concerned with this counting, this difference in a different way. We're more concerned with the factor pair that's associated with it, with this LD function. Now we suppose that the LD function were generalized to allow for more than 2 factors of n. So we take the number 24, for example. Could be represented by a 3 by 8 rectangle, a 2 by 2 by 6 cube, or a 2 by 2 by 2 by 3 four-dimensional prism. So in this case, when choosing the so-called m-dimensional prism of least distance, we use the GLD function, the generalized least distance of m, which is given by the following equation. Remember, the GLD function, like the LD function, is not as concerned with distance through space as it is with counting units away from the origin. Think about it like that, because we're more concerned with the factor m tuple. And you see in the definition we subtract m there. And that's precisely why, because we're counting, not measuring an actual physical distance. This brings us to our first theorem, which states that the GLD of n is equal to the sum of prime factors of n minus the prime omega function of n. The prime omega function is the function that counts the number of primes with multiplicity in the prime factorization of a given number. This provides an easy formula for solving for GLD of n, but the same is not so easy to achieve for LD of n, as we'll come to discover. Theorem 2 brings us to our first pattern that we could see in the LD grid. You'll notice that all the square numbers seem to fall on this diagonal, and only the square numbers appear on this diagonal. So, the statement of the theorem is for n squared, LD of n is equal to 2 times the quantity square root of n minus 1. And all that's saying is that every square number appears on this diagonal. To prove, we consider n equals xy and find the minimum of a d function of x and y equals x plus y minus 2 by taking the derivative of that d function written in terms of x. Now, what other patterns are visible from our LD grid? Well, our third theorem brings us to another pattern that's apparent, in which we notice that the prime numbers are found on the bottom row of this grid, and only the prime numbers, with the exception of the number 1, are on this bottom row. So the statement of theorem 3 is that for p prime, LD of p is equal to p minus 1. And what that basically means is that all the prime numbers appear in this bottom row, and only the prime numbers appear in this row. So from theorems 2 and 3, it follows then that the LD function is bounded by n minus 1 and 2 times this quantity square root of n minus 1 for any given value of n. So as n goes to infinity, the LD function varies between high points for prime numbers and low points for square numbers. Theorem number 5. How can we solve for LD of n? Well, this theorem gives us a practical way for solving LD of n by finding the two factors that are closest together. The statement of this theorem is that LD of n is equal to a plus b minus 2, where n equals ab are positive integers, if and only if a and b are the factor pair that are the closest together. So now we don't have to write out every factor pair when solving for LD. Just find the two that are closest together, and there you have it. Theorem 6. We notice another pattern similar to the one in theorem 2, where the square numbers appear in this yellow diagonal, but also every square number minus 1 appears on this brown diagonal. So where you have 225, you'll have 224. Where you have 144, you'll have 143. So the statement of this theorem, LD of n squared equals LD of n squared minus 1 equals 2 times the quantity n minus 1. And the proof follows from the fact that n plus 1 and n minus 1 are the factors of n squared minus 1 that are closest together, which we obtained from our last theorem, theorem 5. Still, what more patterns can be observed from the LD grid? Now, theorem 7 is where it begins to get interesting. We have this pattern occurring at every prime number on the grid. These long, unbroken lines, they get to a certain point where they break off of this line right up and to the left right there. And you'll notice it happens at every prime number, and it only appears to happen at the prime numbers. So the statement of this theorem is that for p prime and n less than 2p plus 2, where n is a positive integer, we have LD of Pn equals P plus n minus 2. For n hat equals 2p plus 2, which is the point at which these lines break, we have LD of p n hat equals 3p minus 1. This is a very interesting pattern which gives us an insight as to how multiples of prime numbers up to a certain value behave in the LD function. You'll notice a similar pattern in theorem 8, where we have multiples of the square numbers within a certain range falling on these unbroken lines until a certain point where they break. And you'll notice the brown square is the point at which they break. So the statement of this theorem is for all natural numbers n, and k is less than 2n plus or minus 1 equals k hat such that k is a positive integer, we have LD of the quantity n squared plus or minus k times n squared equals 2n squared plus or minus k minus 2. Also, LD of the quantity n squared plus or minus k hat times n squared equals 2n times the quantity n plus or minus 1 minus 2. Now, at this point, we've observed several patterns relating to prime numbers, square numbers, multiples of prime numbers, multiples of square numbers, and so on from our LD grid and our LD functions. So now we consider a different visual representation of the natural numbers, again considering a grid. This time, the position or the block at the point xy will be shaded in if x and y are co-prime. If they have a factor in common, that block will be left unshaded. So perhaps the coprimality relationship can be exploited visually to reveal some patterns that relate to the prime numbers. Now, what's this going to look like? And we have the DP grid, which stands for prime density. The prime density grid is the coprimality relationship on display for us to see. You can see that there's definitely some patterns happening there. It seems to be very rhythmic, and there's some lines that are unbroken. There's some patterns within these lines. And in order to formalize our study of these perceived visual patterns, we develop another specialized function called the prime density function, dp of n, the prime density of n, denoted by dp of n, and dp star of n, the fixed prime density of n, which is so named because dp star of a prime number value is always going to be 1. And these functions you'll see are highly related to Euler's totient function, phi of n. We also obtain the prime density area function, which serves to describe the relative amount of shaded area in the dp grid from the first column up to the nth column. So if you'll think about the prime density functions that we saw previously describing the relative amount of shaded area within a single column, the dp, big dp of n, keeps a sort of running tally. So it's, as you might expect, highly related to the summatory totient function, big phi of n. And unlike dp and dp star that we saw previously, which vary with different n, big dp of n, the prime density area function, is roughly equal to about 2/3 for up to n equals 100. So it definitely tends toward a certain value. Now the limit of big dp of n as n approaches infinity is of interest, but beyond the scope of this research. So we have some prime density function identities obtained through simple algebra, which go to show that these functions are highly related to one another, and these may be useful in proving theorems or in solving for values. And we have some properties of dpn and dp star of n. Theorem 9 states that for p prime we have dp of p equals p minus 1 over p, and that for all composite numbers dp of n is less than n minus 1 over n. So for a given n, n minus 1 over n is an upper bound for the dp function. Theorem 10 states for p prime we have dp star of p equals 1, and for all composite values, besides of course the number 1, we have dp star of n is less than 1. And that goes back to definition, fixed prime density. That's why it's fixed, because dp star of every prime number is always fixed at 1. It was defined in such a way. Now, theorem 11 is interesting. The proof follows from the fact that Euler's totient function is multiplicative, but what this theorem shows is that the prime density functions are in fact highly related to the prime numbers, and thus the behavior of the dp grid is related to the distribution of the primes in an abstract way. So when you look at that grid, you really are seeing the prime numbers at work. And this theorem encapsulates that. The prime numbers are on display in the dp grid. Maybe in an abstract way. Maybe it's a way that's not so easy to recognize upon first glance, but it's there, and this theorem proves that. Now, we consider the relationship to the prime counting function of these specialized functions that we've developed over the course of this thesis, the LD, GLD, DP, and DP star functions. Now, these do not provide a practical formula for pi of n in the following theorems. It's nothing groundbreaking, but it's just meant to algebraically demonstrate that the behaviors of these functions in this thesis are deeply connected to the patterns of the prime numbers. Okay, so theorem 12, we relate the prime counting function to dp star, dp, and the totient function using the floor function. These are fairly easy to prove because you'll see that the summand of each of these is equal to 1 only for prime numbers and the number 1. Theorem 13, similarly, we relate the LD, GLD, prime omega, and divisor functions to pi of n. Once again, fairly easy to prove because the summand is equal to 2 only for prime values. Besides, of course, the number 1, which is why we subtract at the beginning. In theorem 14, similarly, we relate the LD, GLD, prime omega, and divisor functions to pi of n using, again, the floor function. Fairly easy to show because the summand is equal to 1 only for prime values. So in conclusion, the LD grid and DP grid both have revealed visual patterns that have special relationships to the prime numbers. We've been able to formalize our observations through our mathematical study of the specialized LD and DP families of functions. And we've also established the basic functional relationship between the least distance and prime density functions to the prime counting function. So we've investigated some visual representations, a new geometric basis. We've developed specialized functions in order to make sense of these things, and we've arrived at some very interesting conclusions. It's unclear at this point whether or not these grids, the LD and the DP grid, whether or not these functions have any application to the study of the prime numbers, or if there's what that application might be. But future research should consider the development of more diverse visual and geometric representations of the natural numbers in order to reveal the more hidden patterns that were missed in this thesis. That's all I've got for you today. Thank you very much. Once again, I'm Nicholas Adduci, and this has been my honors capstone presentation for Youngstown State University, spring 2021. Thank you.